I'll bet not many of you see any very close connection between this vibrating rope and the hydrogen atom. Perhaps it'll surprise you to learn that there's more connection between the real hydrogen atom and this vibrating rope model than the planetary model we're all familiar with. We appreciate very much you all coming to hear this lecture today, and we're making this film to help make the transition between this rather abstract quantum mechanical view of the hydrogen atom that you've just seen in this film and our more familiar planetary model. I'll refer today to this classical and traditional planetary model by that name rather than the Bohr atom, but I want you to know that they are the same. However, I don't want you to associate any of the criticisms that I make of this model with the name Bohr, because I don't want to depreciate in any way the very important contributions he's made to our knowledge on this subject. By the Bohr atom, or planetary model, I mean this familiar atom consisting of a proton, a positively charged nucleus, and an electron. This model envisages the electron moving about in some sort of a cyclic motion in which there's a balance between centripetal force and Coulombic attraction. Bohr's important contribution was to recognize that this motion is quantized, and he proposed that the quantization is through quantization of the momentum, which is symbolized usually as P, and he proposed to explain the hydrogen atom spectrum that this momentum was quantized in units of h over 2 pi, in which the integer n could take on the values 1, 2, 3, 4, and so on. The importance of Bohr's contribution was that he provided the first explanation that had any usefulness at all of the hydrogen atom spectrum. And of course, it helped a great deal the break with classical mechanics. However, we don't live in the times of Bohr and the necessity to break with classical mechanics, and it's timely now to see where we are today in our understanding of the hydrogen atom. And I want to begin by telling you some of the respects in which the Bohr atom, or planetary model, is in discord with experiments. Now, you recognize this is the most fundamental complaint I can make against any theory, is that it is actually in discord with experiments. I'll also add some respects in which this model is in discord with quantum mechanics. But that, of course, is in discord with another theory, and that's not as fundamental. So let me begin by telling you the respects in which the planetary model is in discord with experiment. The first respect is in connection with the electron distribution in the atom. There are three types of experiments that I'll mention in which we have some experimental feeling for the distribution of the electron in the atom. The first that I want to mention is in connection with nuclear magnetic resonance studies. NMR is the abbreviation for nuclear magnetic resonance, and in particular, the so-called spin-spin interactions. These interactions are commonly interpreted in terms of the quantum mechanical view of the atom because they seem to be connected with the fraction of the time the electron moves very close to the nucleus. And that is a respect in which the planetary model is in direct discord with this experimental evidence, because the planetary model, of course, in its orbiting trajectory, never brings the electron close to the nucleus. The same sort of effect that is represented in the nuclear magnetic spin-spin interactions has shown up somewhat earlier, in fact, in atomic spectra. Once again, the spectral features in which I'm speaking require the interpretation of the electron movement somehow bringing it very close to the nucleus for a certain fraction of its time, and this in discord with the planetary model. The third that I want to mention is perhaps conceptually the easiest to grasp, and that is what is called K-capture. It's a type of nuclear decay in which a so-called K electron, that is a 1s electron, is actually captured by the nucleus, and conceptually it's plain that such a capture implies that the electron comes near the nucleus, which of course is very small, and permits the capture. So these three pieces of evidence have to do with the electron distribution in the atom. They all suggest that the electron comes very close to the nucleus in discord with the planetary model. The next, and perhaps more important to a chemist, area of discord is in the inability of the planetary model to explain many electron atoms. After the Bohr proposal that momentum is quantized, this same idea was applied to many electron atoms by the most prominent physicists of the day, and their results were a total failure. And the inability of that model to extend to many electron atoms is aggravated even more from a chemist's point of view by the fact that it also failed to explain the existence of molecules. So in these very important respects, as far as a chemist is concerned, the planetary model gives him no help. There's one final area of discord with experiment I want to mention, and that is the failure of the atom to radiate its energy. An electron moving in a circular path is expected on the basis of classical electromagnetic theory to radiate energy, and as such the electron would spiral in toward the nucleus. It does not, and restraining the momentum to quantized values, but retaining a model in which the electron cyclically moves around the nucleus, leaves one with the inability to explain why it does not radiate. So that represents, again, a discord with experiment. Now, I want to pass from this discord with experiment to discord with quantum mechanics. Now, here we are not making as fundamental a criticism of the planetary model. And the only reason with which we would regard this type of discord as a very serious matter is because the quantum mechanical model proves to be very effective in explaining these experimental facts here. But since quantum mechanics is successful in explaining these areas of failure of the planetary model, it becomes interesting to us that the planetary model is in fundamental discord with quantum mechanics. And the particular one I want to mention is in regard to momentum, because momentum and its quantization represents the cornerstone of the planetary model. With the quantum mechanical model, the one you've seen described in the film, the momentum on the average can be calculated. And it turns out to have different values than those used by Bohr to get the stable orbits. In particular, the quantum mechanical model, instead of relating momentum to n, an integer, times h over 2 pi, relates it to L times L plus 1, a secondary quantum number, and its square root. This is the value of the momentum ascribed to the atom in its various states, and L can take on values from 0 up to n minus 1. And for example, when n is equal to 1 in the quantum mechanical model, L then must be 0. And so the angular momentum associated with the 1s state is 0 in the quantum mechanical model, rather than 1 as Bohr had to assume. And the value associated with n equal to 2 can be either 0 or 1. If we pick the value 1, it'll be 1 times 1 plus 1, or 2, so the square root of 2. So this will be 1.41, and so on. We find that each one of the possible momenta ascribed to the atom by the quantum mechanical model is an actual disagreement with this most fundamental aspect of the Bohr model. Now there's one final discrepancy with quantum mechanics I'd like to mention, and that is one which is connected with the trajectory. Now I'll put this in parentheses to indicate that we don't have an actual discrepancy here in this sense. Quantum mechanics does not say that the trajectory of the planetary model is incorrect, because quantum mechanics doesn't tell us the trajectory of the electron. Instead, it omits trajectory as an idea, as you'll see in my words in a moment. And so, in a sense, there's this discord that the trajectory is a very important and significant part of the planetary model, and we discover that the trajectory is lost in the quantum mechanical model. Now let me turn to the quantum mechanical view, and what I'd like to do in this particular part of the discussion is to make some connection between classical mechanics and quantum mechanics, but without going into all the detail and the mathematics. In the first place, the quantum mechanical model begins with the classical equations: kinetic energy plus potential energy equals total energy. This would represent a quantum mechanical statement about the motion of an electron in the presence of a proton. And of course, the potential energy would be just the familiar E squared, charge on the electron squared, divided by r, the distance between the electron and the proton. The potential energy, the kinetic energy, if you'll allow me to express this in one dimension, would be just 1/2 mv squared. But for our purposes, it will be convenient to rewrite the kinetic energy in terms of momentum p. So I'll rewrite this as 1/2m times m squared v squared minus e squared over r, because now m squared v squared represents the square of the momentum. And I'll write that as p squared over 2m minus e squared over r equals e. This represents then the classical description of the motion of an electron. Now, quantum mechanics can be connected very simply to the classical equations merely by replacing the momentum, wherever it appears in this equation, by an operator of a differential form. And I won't bother you by writing this, but I'll symbolize it by an abstract symbol, which I'll call delta squared, over 2m, this being a symbol which represents a change from the classical equations into a new differential equation. The potential energy I'll carry down without any change. This is the familiar Coulombic attraction. The force goes as 1/r squared. The potential energy is 1/r. And now I'll modify this equation further by recognizing that a differential operator needs something upon which to operate, and I introduce the symbol c, the wave function, so-called. And of course, I have to introduce it on the other side. Now I have a differential equation which has certain solutions, and these solutions are made quantized, that is, eigenvalues are obtained when I impose upon the equation boundary conditions. Now, I began this lecture with the demonstration of a vibrating rope to indicate the type of differential equation and the type of boundary conditions that are represented in this equation. This is the Schrödinger equation, and a very similar type of differential equation is used to describe a vibrating rope. And the important point is that the application of boundary conditions cause the solutions of this equation to become quantized naturally. The boundary conditions in the case of the vibrating rope were the stationary positions at the ends. In the case of the Schrödinger equation, the boundary conditions have to do with physical reasonableness. That is to say, if we're going to look for the electron, we will expect to find the probability of finding it at infinity, a very, very great distance from the nucleus, go to 0. That's one of the boundary conditions that causes this equation to be quantized. Now, this is a very simple recipe. Any classical system can be written in this form, and the transposition to quantum mechanics can be made with just this substitution. Notice that the potential energy comes down unchanged, and the kinetic energy comes down in an entirely new form. The result is an equation which, when solved, gives exactly the right energy levels for the hydrogen atom. So here you see the model was as successful as the Bohr atom. It reproduced exactly the energy levels of the hydrogen atom. But for our purposes, what is much more important is that this model also reproduces the energy levels of the hydrogen molecule. Now, I have some calculated and experimental numbers for 2 molecules to give you an idea of how successful the quantum mechanical model is. In the first place, I consider the ion H2+, 2 nuclei with a single electron. And I ask, what is the energy to break that bond to give us 1 hydrogen atom and 1 proton? And the other molecule I'll consider is the 2-electron molecule, H2. And I'll consider the energy necessary to break that chemical bond and give 2 hydrogen atoms. And the calculations, based upon this same model that I've talked about, the quantum mechanical model, but now including 2 nuclei and 1 or 2 electrons, give us 64.25 kilocalories, 108.3 kilocalories for the calculated bond energies. In contrast, the experimental values are 64.37 and 108.7. Now, of course, there are uncertainties in both the calculated values. That is to say, these are very difficult calculations, and one has to make certain approximations along the way. And of course, there is experimental uncertainty in these numbers. And what we can say is that this agreement shows that quantum mechanics can explain the existence of chemical bonds. Now, that's very important to a chemist, of course. This means that he's working with a model which, at least potentially, has the opportunity to explain chemical bonding. Now, the characteristics of the quantum mechanical atom that are important to us in talking about atoms and molecules are these. In the first place, the potential energy has come through without any modification. The implication of this is that when we talk about the electron in the atom, the potential energy recognizes the existence of a position. That is, R refers to the distance between the electron and the nucleus. And without any reference to the Heisenberg uncertainty principle, which is concerned with whether one can actually find the electron, this equation tells us that the model implies the electron has a position. The kinetic energy, in contrast, has been very seriously distorted. We've lost the classical momentum and substituted a differential operator, and in so doing, apparently we have lost the trajectory. That is, in quantum mechanical pictures of atoms and molecules, it is no longer profitable to talk about trajectory. Those 2 aspects of the quantum mechanical model are rather unfamiliar. The next aspect I want to mention is still more unfamiliar, and that is that the information about the electron position comes in terms of probability only. Having lost the trajectory, we can no longer make positive statements about just where the electron will be at a given instant, nor where it will be at one instant just after another instant in which we have located it. So position of the electron turns out to be given to us by this equation only in terms of probability. I might note that in contrast to the planetary atom, in which quantization was imposed quite arbitrarily by Bohr in terms of this momentum restriction, in this particular type of presentation, quantization turns out to be a natural element of the mathematical form used. And so one can say with a little more confidence that quantization, or the special energy values of atoms and molecules, are naturally explained by the quantum mechanical point of view. And then finally and practically, the important thing about quantum mechanics is that it fits the experimental data for atoms and molecules insofar as we're able to carry out the mathematics and make the experimental measurements. It takes care of the electron distribution so as to explain the fraction of the time the electron is close to the nucleus. It permits us to calculate the energy levels and properties of many electron atoms. We can calculate for molecules such properties as the bond length, the bond energy, the vibrational frequency, the dipole moment. So, in effect, all of the important properties of molecules can be calculated, provided the mathematics is tractable. The failure to radiate, which is a thorn in the side of the planetary model, turns out to be taken care of in a sort of a backhanded manner by the quantum mechanical model. You see, the failure to radiate is connected with the trajectory which is assigned to the electron, and the trajectory has disappeared from the quantum mechanical model. So the reason that one might expect the electron to radiate and lose its energy is no longer present in the quantum mechanical point of view. Well, then you see that this model is a very successful model from a chemist's point of view, and very important to a chemist because he's interested in bonding, and he must deal with a model which permits him to explain bonding. There are a number of questions that naturally come to mind. One, for instance, is why has the planetary atom persisted so long? Why do you find it so often represented in the textbooks of the day? I mean college-level textbooks as well as high school textbooks. I mean physics books as well. I have my own answer to this, and there's no way of being sure I'm right. I feel that the answer to this question, the persistence of this planetary model, is connected with the difficulty of making a bridge between the very familiar and very easy trajectory model associated with the planetary atom and this rather abstract and unfamiliar probability view of the atom. I think that the Bohr atom does serve as a bridge for those of us who lived for many years thinking that the planetary model was an acceptable model, and then having these roots torn up and tried to take a more modern and more useful point of view concerning the atom. And here I appeal to you to remember that the student you're teaching has not had the planetary model instilled into him and given a position of credibility by having teachers tell him this is a correct model. And consequently, he doesn't need this bridge. And in fact, the opposite situation exists. He is aided by taking a more up-to-date point of view of the atom so that he won't need the bridge later. To be sure, this is an abstract point of view, this quantum mechanical model, but he will sooner be able to understand it and comprehend it, and of course then to aid in its evolution to a still more advanced view if he is not taken back to the point of believing in this very easy model, which is in serious disagreement with experiment and not in qualitative accord with our up-to-date model. So I feel that this bridge is needed by us, the teachers, not by the student. And so we're not doing him at all a favor in building in this erroneous view, so he'll need the bridge too. Now, one of the questions that I'm usually asked when I talk about the quantum mechanical atom is, how does the electron get through the nodal planes in order to move from one side of the atom to the other? And I just mention this to indicate to you that any question which you ask of the quantum mechanical view, which is a trajectory question, is not going to be answered. And that is a trajectory question. It's like asking this vibrating rope, how does one antinode of the rope get to the other side through the nodal position? And of course the answer there is, that's a silly question. It doesn't get through the node. You're asking a question which is inappropriate. In the same way, the quantum mechanical orbital tells us the probability of finding the electron. And consequently, it is not a useful question to address to it trajectory questions, and that's one. Just as it is not useful to ask it, why doesn't it radiate? The question of why doesn't it radiate stems from assigning a trajectory to the electron, and this one doesn't. Well, that's typical of many questions that cause confusion, and I feel that one avoids confusion and difficulty by presenting early in the student's scientific career a model which we believe is useful in experimental aspects, that is, in explaining experimental results. And the student won't be asking questions which are inappropriate if he doesn't have this model built in. He will be working then with a model which will permit him to go ahead and explain properties of many electron atoms and molecules, and this, of course, is the purpose of a course in chemistry. Perhaps some of you have questions. Yes?
To my students, it would seem that the inclusion of the kinetic energy in this formula would imply motion and consequent acceleration and radiation from the atom. How then is this argument of failure to radiate on the part of the planetary atom a good argument to the students?
Well, I too am confronted by this question with freshman students, and there isn't a very ready or obvious answer. In the first place, this quantum mechanical model does very definitely convey the idea of kinetic energy. That is, one can predict from this model the average kinetic energy, and I associate this naturally with the existence of trajectory and motion. And there's no clear-cut way to dissociate kinetic energy with motion in my mind. I am relieved a little bit from the necessity of explaining why the electron doesn't radiate, because I know nothing of this motion. I know nothing in the quantum mechanical model of the trajectory. And consequently, when I say, why doesn't it radiate, I'm not sure that it should. I don't know the trajectory. I feel that perhaps my difficulty with this, and I take it your difficulty in explaining this, is somehow connected with the fact that to me, kinetic energy automatically leads me to think classically, in which kinetic energy implies motion and trajectory. And it may be that a student who is raised from his earliest scientific explanations with a quantum mechanical view in which trajectory questions are never valuable won't have so much difficulty with asking trajectory questions. And then, of course, he'll be better prepared to carry this on to the next step and improve it some more. Sir?
Professor Pimentel, can you give us more information about the letter C?
You refer to this symbol, this Greek symbol psi. It conveys all we know in quantum mechanics about the position of the electron. And for our purposes, we are interested in its square. The square of the quantity psi gives us the distribution which you saw in the film, the probability distribution. And I connect the square of psi with the word orbital, rather than complicating the student's life by connecting the word orbital with the solution to the differential equation. We cannot sense psi directly, only its square. So the answer then is its square tells us the position of the electron, and this is what is conveyed in the picture of the orbital. Any other questions?
Is it acceptable to think of the electron distribution as a charge cloud?
Well, there is a real element of cloud aspect to the orbital picture, as you saw in the film. associated with the square of this quantity psi. For my own purposes, I don't like to use the words charge cloud because there is a semantic meaning to this that is inappropriate. In particular, the word cloud suggests dispersed over space. And in terms of the analogy of the hummingbird, it would correspond to squashing the hummingbird and spreading him all over the field. And of course, that isn't the meaning of that plot of his positions, and that isn't the meaning of the probability plot. It's a probability cloud, not a charge cloud. You see, the charge is at any instant, according to this potential energy term, at a position, not dispersed in space. Well, in conclusion, then, let me thank you all for coming. I realize that a short talk like this cannot possibly answer all of your questions. Furthermore, this is a very difficult area. The transition from the classical trajectory model to the quantum mechanical model is going to be very difficult to make. That's the reason that I'm interested in speaking to audiences like yours, and the reason that we're making this film. If we have helped you at all in moving ahead to a more useful and meaningful model, then this film will have justified itself. And you should realize that it won't be easy for any of us to teach the quantum mechanical view, but in the long run, we must move ahead as the scientific view advances. Thank you.